This is 6.2.2 part 2, the ideal gas equations. We're going to start by introducing a new concept of measuring the amount of something called the mole. So first let's visualize one atom of hydrogen, or rather I'm going to visualize its nucleus because the electrons are so small they're irrelevant to this case. So here's hydrogen with 1 proton, and then here's helium with 2 protons and 2 neutrons. So the mass of this helium is 4 times the mass of the hydrogen. So if I had a glass that was full of hydrogen atoms, and I had a glass that was full of helium atoms, in this situation, I can't use the mass to say how much hydrogens there are or how much heliums there are. Because helium is 4 times as massive as hydrogen, if they have the same mass, there will actually be less helium atoms in that glass, the hypothetical glass. So we start to use something called the mole. That helps make it easy for us. So 6.02 times 10 to the power of 23, and these are atoms, is inside 1 mole. So this number is called Avogadro's constant. And we use the symbols Na for Avogadro's constant. Now, physics students who don't do chemistry always find this concept a bit confusing. So in this new quantity that we call the mole, in 1 mole there are 6.02 times 10 to the 23 atoms. It doesn't matter what atoms they are, whether they be hydrogen, whether they be helium. As long as there are 6.02 times 10 to the 23, that is 1 mole. So if there are 2 moles, it will be 2 times that. If there are 3 moles, there will be 3 times that amount. Yeah? So this many atoms is in 1 mole of a substance. And 1 mole of hydrogen has a mass of 1 gram. And 1 mole of helium has a mass of 4 grams.
You can have 1 mole of carbon dioxide, and that's not considered 6.02 times 10 to the power of 23 atoms, but molecules instead.
Yeah, because it's carbon dioxide.
Yeah.
But that's a molecule.
Yeah, but this isn't just for atoms though.
Because we're dealing with just atoms. Yeah? So here we're dealing with single atoms. We're not dealing with polyatomic gases. Yeah? Our ideal gases are all monatomic. So in that regard, in chemistry, because you're dealing with molecules and stuff that's polyatomic, then you're dealing with molecules, but we're dealing with just atoms. Okay? So our whole concept starts with being an ideal gas. Hence, one atom in each molecule of gas. So, the equation that links these together is the number of atoms, or number of molecules if you're using polyatomic molecules in chemistry, is equal to the number of moles times by Avogadro's constant. Or N equals to N times Na. So N is your number of atoms or molecules, which has no units. Then N is the number of moles, which has units of mole. And Na is Avogadro's number, which is 6.02 times 10 to the 23 per mole. Then we've got another value called the molar mass, which is the mass per unit mole. So for that, we say that the molar mass is equal to the mass divided by the number of moles. And if we know this, we can make another equation in relation to that. Because using this, we've got N is equal to mass divided by the molar mass. And then if we go back to N equals to N times Na, and we substitute this in, we get N equals to mass over molar mass times by Na. And the molar mass is measured in kilograms per mole. Okay, let's start a new page. So now I will give you the ideal gas equations in two situations or two scenarios or two different ways of looking at it. So the ideal gas equation for N number of moles is PV. Now, if you remember from part 1 of 6.2.2, we did PV equals to some constant multiplied by temperature. That constant is equal to N times R. So we get PV equals to nRT. So number of moles, and this is called, R is called the molar gas constant. So N is number of moles. And R is the molar gas constant. which is equal to 8.31 joules per mole per Kelvin. Then we'll do another ideal gas equation, but this time it's for an n number of atoms or molecules if you're working in polyatomic situations. And here that constant, the same constant, is PV equals to NKT. Now this K that I've written here is not the same K that we did in 6.2.2 part 1. The K's that I was writing there was an arbitrary value, whereas this K represents Boltzmann's constant. So N is the number of molecules or atoms, and it has no units, and K is the Boltzmann constant, which is equal to 1.38 times 10 to the minus 23 joules per Kelvin. Now, if we look at these two equations and compare them together, we can see that the only difference is the NR and the NK. So that means that NR is equal to NK. So NK is equal to NR. And you remember that we said that big N is equal to little n times by NA. So we can make that substitution. So big N here is equal to little n times by NA times by Boltzmann's constant is equal to n times the molar gas constant. So now looking at this, the little n's will cancel out. So Avogadro's number multiplied by Boltzmann's constant is equal to the molar gas constant. And then getting towards the end, we'll now look at the work done by or on a gas. So let's think about this for a moment. Work done. Work done is force multiplied by displacement in the same direction as that force. Now, if we have a gas who has a pressure and then there's a change of volume, that means there's some kind of a displacement. And if there's some kind of a displacement and pressure is caused by a force, that means a force has caused a displacement, and so work has been done, either by the gas or work has been done on the gas. So let's look at the first diagram. If volume of a gas changes whilst keeping the pressure constant, we have a diagram which looks like this. So we've got P, V, and then we've got 2 points that we'll call A, and we'll call B. Now, moving from A to B, means that there was some change in volume. So here is delta V. And here there was some value of pressure which didn't change. So the work done by moving this gas from A to B is the area under this graph. That's the work done. So in this case, it's work done, W, equals to pressure times by the change in volume. So let's think about this for a second. If the volume has increased whilst maintaining a constant pressure, what does that mean about the system? Was it gaining heat or was it losing heat? So in this case it was gaining heat because temperature must have increased for that to happen. So in this case, work was done on the gas, not by the gas. If we went from B to A, so imagine, for example, a balloon, and if that balloon is shrinking but maintaining constant pressure, then that means its temperature must have gone down. That means it's losing heat to the outside. So the work is being done by that gas onto something else. Now, if we have a case where we don't have a straight line, in the example that we might have some sort of a curve, then the work done is still going to be the area underneath that graph. Now, in this case, pressure is a function of volume. So the work done here would be equal to the integral of pressure as a function of volume, and we integrate that with respect to volume. Our limits going from VA to VB. And in this situation, because pressure is changing, actually temperature might be constant. And if temperature is constant, we'd call that an isothermal process. So 3 words that I'll say right now. Isothermal means that the temperature doesn't change. Isobaric means that the pressure doesn't change. So the word iso means the same, ISO. So let's write this out. PV equals to NKT. If we rearrange that, P is equal to NKT over V. So it's NKT all over V dV. So if you were to integrate 1 over v, you'd get ln. So that's nkt ln v, remembering to include our limits. Now here, we are assuming a constant temperature. And we might not have constant temperature. So, in a case where you don't know if it's constant temperature or not, or you're given some kind of arbitrary curve, which might not even be following nkt over v, because there might be some other processes going on, you need to work out the area using numerical methods. For example, trapezium rule. So using trapezium rule, if we have a similar kind of curve, and it can be for any curve really, what you first want to do is you want to look at the values that you have on the x-axis and see if you can split them up into equal strips of a good thickness. Now, depending on how curved your line is, you might find that having only 2 strips suffices. You might find that you might need more than 2 strips. You might need 3 or 4 or 5. So you analyze the x-axis and decide what's the most appropriate number of strips to have. If you have too many, it's going to take you too long in the exam. If you have too few, then you're going to have a massive over or underestimate depending on your curve. So in this case, let's just say we split it into 4 equal strips. So split into 4 equal strips of width h. So each one of these has a width of h. Then we want to read our values for y-axis. So here we'd have y0, and at the bottom we've got yn, then we've got y1, y2, y3, etc. Now if you have more strips, then you can go on forever. In this case, my yn is just y4. And then we use the formula for the trapezium rule. So the area is equal to h over 2, so your width over 2, and you multiply that by y0 plus yn plus, then you have 2 lots of the sum of all the y's in between. So all the y's in between we label as yi, and we're going to start from yi equals to 1, and we're going to finish at n minus 1. So if we read this in the English language, it's your first value of y, your last value of y, plus 2 times the sum of everything in between. So in this case, it would be h over 2, bracket, y0 plus y4, because y4 was my last one, plus 2 times, bracket, y1 plus y2 plus y3, close bracket, close bracket. So, in this example, A is equal to h over 2, y0 plus y4 plus 2 times y1 plus y2 plus y3. And doing that will save you the trouble of having to count squares in the exam, which can not only be frustrating because it takes so long, but actually sometimes when you're counting that much, you lose track of what you've counted. So this is a better way, and there's less chance for you to make a mistake doing it this way. And that's the end of 6.2.2.